the Software Engineering Radio, Episode 3, interview with Doug Schmidt. Welcome to this episode of Software Engineering Radio. This is Markus Völter. Unlike the previous two episodes, this one is one of our interviews. Our guest today is Douglas C. Schmidt. Doug is a professor of computer science at the Vanderbilt University. He focuses on middleware, distributed real-time embedded systems. He's actually the father of the DAU Orb and the ACE middleware below it. Doug is also well known for his work in the patterns community. He is co-author of the Pattern-Oriented Software Architecture Volume 2 book, which deals with patterns for concurrent and distributed objects. More recently, Doug has been focusing on the integration of model-driven software development and middleware. He has written a guest editorial in this February's edition of IEEE Computing. It provides a nice summary on Doug's view on these topics. At the OOP 2006 conference in Munich, I gave a tutorial together with Doug on the state of the art of model-driven software development. The evening before the tutorial, we got together in a hotel room and recorded the interview. Have fun. Doug, welcome to Software Engineering Radio. Why don't you start by explaining a little bit about your personal background and what you do in real life?
Thanks, Marcus. I appreciate your interviewing me. First of all, I've been a professor for the last decade or so at Washington University in St. Louis and University of California, Irvine, and now at Vanderbilt University. But in some sense, that's really just my hobby. And what I like to do most is spend time working with people building systems, building software, building open source software, using the software for building actual applications. And I managed to get into this field sort of through an unusual route. My original background was in sociology, which is the study of human organizations and behavior and structure of organizations. When I got done with my bachelor's and master's degree in sociology, I realized that while I enjoyed it intellectually, there was very little way to make a living doing those kinds of things. So I managed to get into a PhD program in computer science at University of California, Irvine, where I got my PhD in software engineering and networking. And when I finished up my degree, I realized that a lot of very smart people had thought about networking topics for a long time. And so I decided to focus instead on what in those days was the beginnings of what we now call middleware. And so when I went to be a professor at Washington University in 1994, we started doing a lot of work on middleware. And in fact, one of the very early sponsors of our work was the German company Siemens, in particular the group up in Erlangen that does work on medical engineering solutions.
You mainly work in the domain of distributed real-time embedded systems, or DRE systems. Can you tell us a little bit about those systems and the particular challenges in developing them?
There are a number of different definitions of what a DRE system is. One of my favorites is a DRE system is a system where the right answer returned too late becomes the wrong answer. And they're systems like shipboard computing or avionics or process control, manufacturing, even to some extent things like financial services and parts of telephony and other domains along those lines, where if you get the information there too late, it doesn't have much value for its user, either because the stock has changed price and you've bought something too high or too low, or because the device you were trying to control in the physical world has been destroyed because you were unable to prevent it from moving in a direction you didn't like. The characteristics we've been looking at most recently have really been on so-called enterprise distributed real-time embedded systems, or enterprise DRE systems. These would include things like supervisory control and data acquisition systems for power grids, total ship computing environments, large-scale information command and control systems, and so on. And these types of systems are characterized by the latency and jitter requirements that you might expect from a real-time embedded system, low latency and very predictable low jitter, as well as also having characteristics of being highly scalable that you might expect from an enterprise distributed system. And these kinds of systems are extremely difficult and complex to build if, for no other reason, that people often don't have a very good idea of how they're supposed to behave until they have them largely fielded, which means that any mistakes in problems that they have in the design and the architecture and the implementation are often done so far in the life cycle that it's very difficult to try to improve them and evolve them and optimize them to work properly. So a lot of the work that we've been doing over the past several years has been developing technologies both based on middleware, that is runtime platforms that help to take away some of the complexity of trying to program applications manually, as well as combining them with model-based techniques which try to raise the level of abstraction so people work with abstractions that are closer to the domain as opposed to being close to the technology or close to the solution space. And these particular kinds of abstractions are very important because they allow us to be able to do what's called speculative computing, where you can do all kinds of what-if analysis to understand very early on what the characteristics and quality of service of the system will be, even if you don't have all the parts finished and complete. And we found that these kinds of systems also tend to motivate the need for a lot of advanced R&D capabilities because they are simply far beyond the grasp of any individual or any team to solve with traditional ad hoc, proprietary, and very manually intensive software development technologies. So I guess in a nutshell, the kinds of systems that we work with interface a lot with the real world and also have information systems aspects to them as well, and trying to balance the trade-offs between the constraints of real-world processes and real-world control with the kinds of complexities that arise in information technology and information systems is one of the characteristics that make the enterprise DRE domain so challenging and so rich as a place to explore.
If we look at the term DRE, then the D means distributed. So I guess the middleware in those systems plays an important role. So can you explain a little bit the role of middleware as kind of the backbone of these systems, I suspect?
Sure. If you look at the way people used to build real-time and embedded systems, it gives a good understanding of why these domains are so hard. Historically, people have built these kinds of systems by putting the applications directly on top of hardware, if you go back far enough. And perhaps over the last 10, 15 years, what people typically have done is they've built the applications directly on top of operating systems. Initially, proprietary cyclic executives, and more recently, off-the-shelf operating systems, things like VxWorks or LinksOS or QNX. And one of the characteristics as these systems get larger and more integrated and more distributed is you find that there's a lot of things that are required in order to make these systems work that typically are not part of the experience and expertise base of people who have domain knowledge, the systems engineers, the software architects, or the software developers in those domains. And so what we were observing over the past decade or so was that many times when people would try to build these larger scale distributed real-time embedded systems, they'd often get stuck because they didn't have the right expertise in-house to match the low-level platforms and protocols, the operating systems and the hardware and the buses and so on, with the knowledge of the domain artifacts, things like heads-up display or route planning and navigation if you're in the avionics domain, or being able to do various kinds of sensor management and planning and filtering and track correlation if you're in the shipboard computing domain and so on. And so what was really needed was some kind of technology layer or layers that sits on top of the operating system, on top of the network, on top of the buses and the hardware, but below the specific application services that are part of the domain space. When we first started looking at middleware back in the early to mid-90s, people didn't really have a good idea of what it looked like. It was just kind of a blob that somehow linked things together. And people had examples in those days of things like, say, SunRPC or the distributed computing environment DCE from the Open Software Foundation. As people began to do more work, in particular as a lot of the researchers joined in some of the early efforts on Corba, it became clear that there were actually a number of layers in the middleware stack, just like there are a number of layers in, say, the OSI stack for network protocols or the TCP/IP internet stack for protocols. Some of the layers people typically associate with middleware these days range from what's often called host infrastructure middleware, which is essentially an abstraction of the operating systems and their different heterogeneous APIs. If you think of an operating system, it's basically a silicon abstraction layer. It's abstracting the higher level services and applications from the details of the underlying hardware. But the problem, of course, is that there's so many different operating system APIs to choose from. Even within the Windows family, there's 7 or 8 different variants. Within Linux and Unix, there's dozens of different variants, not to mention the dozen or so common real-time and embedded systems as well. And so as a result, we need something to abstract away from that. So My early work was on this host infrastructure middleware abstraction in the form of something called ACE, the Adaptive Communication Environment. And ACE provides for the C++ world what Java Virtual Machine and the Java class libraries provide for the Java world, or the CLR and the Microsoft class libraries and Win32 encapsulations like Microsoft Foundation class provides for the Windows platform. It provides a way of being able to write at a higher level of abstraction that's not so tightly coupled to the details of any one platform. And this provides things like event demultiplexing, synchronous and asynchronous communication, data transfer, synchronization, locking, concurrency control, threading, processes, managing of various kinds of system resources in a platform-independent way. It turns out, of course, if you start trying to build systems that are going to be connected over a network, you need more than just those basic host infrastructure, middleware, encapsulation building blocks. You really need to have something that's often known as distribution middleware. And distribution middleware's purpose in life is to try to preserve a common programming paradigm, say an object-oriented paradigm or a component-based paradigm or a service-oriented paradigm, and make it look to the application developers on the client and server side like they're making method calls on local objects, when in fact they're actually making calls on proxies, and they're using some kind of broker implementation of the broker pattern to glue together the various parties in the communication path. So distribution middleware includes things like Corba or Java remote method invocation, or even DCOM back in the Microsoft days. Basically, broker abstractions that make it easier to pretend as though you're programming standalone systems when in fact you're talking across a network. The next layer up that's worth characterizing is what's often known as common middleware services. As you start building distributed systems, you'll find that there's certain services that are common and reusable, but very powerful and help to reduce a lot of effort that otherwise goes into reinventing things from scratch. So directory and naming services and discovery services, event services, fault tolerance services, service for handling various kinds of security issues, resource management, load balancing, and so on. These are things that are often reusable by many different applications. Not all, of course, but by many of them. And it turns out that this is one of the more interesting areas of middleware these days, and there's a lot of work going on both in the research world and in the commercial world trying to find the right abstractions for these services. The last layer of middleware that it's worth characterizing in a generic sense is what I often term domain-specific middleware. The other layers, the host infrastructure middleware, the distribution middleware, and the common middleware services are all things that you could expect to find off the shelf or eventually will find off the shelf as the APIs stabilize and the implementations mature. The domain-specific middleware, in contrast, are things that you don't necessarily find off the shelf because they really constitute the intellectual property, they constitute the value-added capabilities that come from companies and groups that work very deeply within a particular domain. So if you work in avionics, for example, you'll have a tremendous amount of knowledge of things like autopilot or route and navigation planning or heads-up display or various kinds of management of devices and such. And those types of capabilities would be very different from the kinds of domain-specific entities you'd get if you were doing some kind of process control system or a financial services system. And so what you typically find is that the domain-specific services are reusable, but their scope is much more localized to a particular vertical application domain. And I think in the long run, this is where a lot of the interesting work remains to be done, not only in terms of the middleware, but also in terms of the supporting tools and languages that help make the middleware easier to apply for domain-specific applications. And I think we'll talk a bit more about this when we get to the topic of domain-specific modeling languages.
Yeah, sure. We'll cover that later. So before we get there, I'd like to get back to the middleware, specifically to Corba. In the non-embedded world, I get the impression that Corba has gone out of fashion, and things like the Corba component model have never caught on in the enterprise world. So I think that's different in the embedded world. You use Corba in most of your systems, right?
We actually do a number of things. We've diversified over the years. We do work now on middleware platforms that involve Corba. Of course, that's been our bread and butter for about a decade or so. We also do some work on Corba component model. I'll talk more about that in a second. But we also do a lot of work these days on the OMG's data distribution service, which is a very efficient pub-sub mechanism that has very nice features that go above and beyond what you're going to find with standard Corba today. For example, the OMG DDS, as it's called, has support for so-called meta events. You can subscribe to the creation of new topics. You can subscribe to the creation of new subscribers. You can subscribe to the creation of new publishers. You can also subscribe to events like network has been partitioned, or quality of service that was requested can no longer be achieved due to various overload conditions and so on. And this makes it possible to build much more dynamic systems that can learn the characteristics of the environment in which they run. Other characteristics that DDS has that are an improvement over Corba is that they really represent a delayered approach to PubSub, whereas in Corba, PubSub is done as a layered service, the event service, the notification service, and so on, built on top of the orb. With DDS, the PubSub mechanism is the orb in a sense, and the orb is subsumed by those mechanisms for doing publish-subscribe. The other thing that DDS has that's really quite interesting, and a lot of our research is consumed with that these days, has to do with the number of quality of service parameters. There's about 24 different quality of service parameters that DDS supports, dealing with things like reliability and resource constraints and history, and trading off reliability with timeliness, and giving coherent views on changes to data structures that are sent across in a PubSub manner, doing various kinds of deadline scheduling requests and latency budgets and so on. And this goes far beyond what you would expect to find out of Corba, or even real-time Corba for that matter. And this is very powerful, but it also means that there's a lot of issues related to optimization and certification to ensure that all the different suppliers and consumers in the system that are tweaking and turning their quality of service knobs to different settings end up with coherent results. So we're really quite excited about DDS as sort of the next step, and we've been collaborating very closely with a number of different DDS providers, including Prism Technologies and Real-Time Innovations and Objective Computing Inc., OCI, all of whom provide different DDS implementations. We also have been doing some work on enterprise Java Beans, and particularly trying to extend some of the deployment configuration mechanisms and services provided by the Corba component model through model-driven techniques to work appropriately in the world of EJB and J2EE as well. So, and I should also mention that one of our students spent an internship at Microsoft recently, so we also have some .NET work going on. Here's kind of the way I look at the world these days. I think you're absolutely right, Marcus, that in the classic enterprise world, the sort of the transaction systems e-commerce side, it's pretty clear that Corba is no longer the new kid on the block, and there's a lot of other technologies that have become very fashionable in those environments, particularly lately things like web services and service-oriented architectures. Where I see Corba still having a lot of value, though, is in two areas. One, of course, is in DRE systems, which are often characterized by the need to be able to have very long lifespans and the need to be able to integrate lots of different technologies running on many different platforms over long periods of time with many different languages and many different characteristics and technology bases. And Corba is really about the only game in town these days that satisfies most of those needs. It's a standard. You get multiple interoperable implementations from different suppliers. It works on many, if not all, operating systems. If you take a look at the totality of the orbs that are available, it works on many different programming languages. And so a lot of people in those domains who look at things from a 5 to 10 to 20 year perspective really like Corba for that reason. And of course it also, especially in the C++ and C bindings, focuses on quality of service and low latency and high throughput and good predictability. So I think Corba's got a very bright future in that space. And you see this reflected in terms of things like software-defined radio, where it's very widely used, and in a lot of the aerospace and defense industries, where it's also very widely used. It's also very widely used in the telecom industry as well. One other place it's worth just noting, because sometimes we forget about this in our pursuit of the big or the small, is just the mainstream client-server applications that need to send information across a distributed system or a network. The kind of places where people used to use, say, RPC or DCE. What I find, especially because of the maturation and the ubiquity of good, low-cost, or even free implementations of Corba, often open source implementations, a lot of people doing just sort of general purpose computing that requires network connectivity often find Corba a very nice solution. I find this especially in places like China and India and other countries where they have a lot of computing infrastructure that they're in the process of putting together, and they don't have to worry about a big installed base, and they're trying to avoid they're trying to hedge their bets by keeping their platform choices open. So we see a lot of people at least using our middleware, from all around the world. And I don't think they're using them for classic enterprise systems, but they're not using them for embedded systems either. They're using them for sort of this general purpose computing that is tied together with network types of applications. But the good news is that as we get better support for higher level abstractions, things like domain-specific modeling languages, which we'll talk about later, to some extent, the specific choice of middleware platform becomes less important. It's always important, of course, but becomes less important or less strategic, and the choice of the right abstraction for programming and integration becomes more important. So where I hope we're going to be in 5 years or so is Corba will be one piece of our overall portfolio of R&D and product activities, but a lot of that stuff will be subsumed by generators out of domain-specific modeling technologies.
You mentioned open source implementations of Corba. One of them is the DAU Orb, which you kind of invented or built initially. Do you want to maybe tell our listeners a little bit about how this has developed, where it's used, and how it evolves today?
Sure. When I was a professor at Washington University, we'd been working on this ACE host infrastructure middleware technology for a number of years. I started working on that actually while I was a grad student in California. And it found its way onto some interesting projects. It found its way into the Motorola Iridium project, which was quite a revolutionary project for the day. It found its way into some various private branch exchange switches and central office switches from Ericsson and some other folks. And at first we were sort of skeptical that Corba was even the right thing to do, because we did a lot of benchmarking in the early days and found that the early implementations of Corba were unbelievably inefficient. They had lots of extra memory copies and lots of extra locks and overhead from threading and other sources of inefficiency and hazards and so on from scheduling point of view. And about 1997 or so, we had built up enough infrastructure in the form of ACE that we decided we would actually see if we could take all the experience we'd learned and gain benchmarking the Corba implementations to see what was wrong with them, and actually try to do a better job of implementing them than the kinds of things that were available at that time. So we took the patterns that we learned and that later got documented in the POSA 2 book, and we took the frameworks that we developed for ACE and the wrapper facades we developed for ACE, and we arranged them to implement a version of Corba, which we called the ACE Orb, pronounced DAU. And this took a couple of years to really get off the ground. At first, it was, as most beta and alpha software is, big and slow and clunky and full of bugs. But one of the great things about the open source community is that you get a lot of really smart people all around the world focusing their brain power on improving that technology base. And we got some really innovative contributions from all over the place. We got a guy from Colombia, South America, who contributed some super optimized event demultiplexing logic that we put into our reactor framework in ACE, which sped up the orb inner loops considerably. We had some people down in Santiago, Chile, contribute some interesting optimizations for encoding and decoding of the common data representation of Corba using assembly language instructions to avoid memory copies. And over the years, a lot of very, very talented people from the United States and all around the world, including Germany, contributed lots of interesting things. And as a result, as of circa 2000, 2001, we had an orb that was competitive in terms of features and competitive in terms of performance with most of what was available commercially at that point. Around that time, a number of companies, including Prism Technologies and Objective Computing Incorporated, and more recently companies like Remedy in the Netherlands, started to support DAU and ACE, for that matter, using a commercial support model not unlike what, say, Red Hat or Cygnus before them had done for the GNU tools. And that's when things really started to take off, because we were able to get a lot of another bright minds who were able to go in and improve the software. A lot of companies started to pick it up at that point, including major projects at many aerospace companies, Boeing, Lockheed, Raytheon, as well as many commercial companies. If you look at almost any Fortune 500 company there, or telecom company, there's probably some DAO poking around there somewhere. And this has ended up allowing us to create a fairly complete and faithful and efficient implementation of almost the entire Corba 2.x spec and almost most of the so-called lightweight Corba component model, or Corba 3.0 spec, 3.x spec. And that's where a lot of our focus is these days, finishing off some of the implementation aspects that go into the Corba component model as it pertains to the profile that was stripped down, removing things like transactions, removing things like persistence to make it a little smaller, to make it a lot more predictable and fast for the distributed real-time and embedded world. So it's been quite an interesting experience being involved, not just from a research point of view, in an ivory tower-like sense, just looking for new innovations and publishing papers, but also trying to make sure that the quality of the software that we developed was sufficient that people could use it for bet your company mission-critical types of systems. One of the things that we've learned along the way is that to be successful in this area, it's crucial to have automated support for quality assurance. And I think this is actually an observation that most successful larger-scale open-source projects like Linux or the GNU projects and so on have discovered. You've got to find some way to be able to take advantage of all those spare computing cycles available in the user community and all those thousands of eyeballs to focus them on solving problems that have to do with places that may not otherwise be exercised through normal smoke testing that people do when they put out their open source releases. So we've spent a lot of time researching in collaboration with colleagues at University of Maryland and a couple of other companies, including Raytheon and Lockheed Martin, ways of being able to automate large amounts of the QA. And we've got it to the point now where we can actually run a very large amount of test cases in a distributed environment using techniques not unlike the SETI at Home project that runs search for extraterrestrial signal contacts through people's screensavers in their spare time. So I think that the take-home point I've learned from this experience over the last decade or so is that you can produce very high-quality software if you're willing to take the time to try to automate the distributed continuous quality assurance and build processes.
You've already mentioned the term pattern, and you're also a co-author of POSA 2, the Pattern-Oriented Software Architecture Series, Volume 2, about distributed and concurrent objects. I think that's the subtitle. So maybe you want to elaborate a little bit about the use of patterns in this kind of systems.
There's actually a kind of a funny story about that. Back in 1993, when I was finishing up my PhD at UC Irvine, I happened to be doing two things at the same time. I was learning the Orbix implementation of Corba, which was used very heavily on the Motorola Iridium project I mentioned earlier. And I was also a reviewer for the Gang of Four book, the Design Patterns catalog. And what was so fascinating about this is I was reading that Design Patterns catalog book, I began to realize that the patterns I was seeing described in this book, which, by the way, had not been published yet, things like chain of responsibility or proxy or bridge or strategy, these were all the same kinds of abstractions I was seeing as I was looking at the Orbix source code. And it really struck me how profound this pattern concept was, because clearly these developers, often Dublin, Ireland, such as Chris Horn and Hugh Grant and some of the other people who developed the early Orbix implementations, had come upon the same design techniques even though they'd never seen the book on patterns, which I thought was quite eye-opening at the time. And I remember thinking at that point, I was kind of stuck at a crossroads in my life, whether I wanted to go to be a professor or whether I wanted to do consulting and work in industry. And I remember thinking, I would really like to be able to go on and at least spend enough time in the academic setting to figure out what types of patterns would be applicable for things like, say, distributed systems and networked applications. Didn't really know that much about middleware at those days, but I guess if I thought about it, I would have used the word middleware. And I wanted to take some time to learn them and write them down. And the ironic part was, over the next, say, 5 to 7 years of my life, I spent a lot of time developing software, working with companies like Siemens and Boeing and many, many other different groups, and learning these patterns and having the fortune of working with many bright students and colleagues like Frank Bushman and Michael Stahl and Michael Kircher at Siemens, and actually finding ways to document these patterns, and then at the same time building middleware and building networked applications that could actually try them out in practice. So as it turned out, one of the reasons why we were able to create such a large amount of software, things like ACE and DAU now are around 2 million lines of C++ code that run on dozens of different operating systems and compilers. One reason why we were able to build such a large amount of software and keep it going for so long with, quite frankly, a rather shoestring budget for a long time was because we were able to leverage the architectural insights that came from using the patterns that we discovered through other work. And that became crucial to help bring new people, new grad students, new staff, new members of the ACE and DAO community into the fold, as it were, and to guide them, to explain to them what the architecture of the system was based on, and then explain to them in pattern form what the constraints were, what the trade-offs were, and help them use those patterns as effectively as documentation to make good design decisions. And I don't think we could have done it had we not had the pattern information. Now, as we've moved on since those days, a lot of that work culminated in the POSA 2 book. We've learned a lot of other things. In fact, one of the things we've learned recently is how you can take patterns for optimization and use them to do so-called specializations of the middleware. There's a classic tension when you build any kind of reusable software between the generality needed to get the maximal number of users happy on the maximal number of use cases and the specificity that comes from wanting to make the software as fine-tuned and optimized for the particular context in which it runs. And for a long time, people have had to choose one of those two ends of the spectrum. They either built things from scratch to be highly specialized, or they would build things in a very reusable way, in which case they were often very inefficient. So what we've been doing lately is working with various kinds of aspect-oriented approaches and other kinds of techniques, such as partial evaluation, and coming up with domain-specific languages and tools that let us take our general-purpose frameworks and be able to customize them for particular details of the underlying platforms, of the underlying environments, and of the use cases the application developers are using. And this, of course, is yet another way of looking at patterns. You're looking for patterns of invariance, what things stay the same, what things change. A good example would be something like the event demultiplexing mechanism that's used in most orbs. In the case of something like the ACE orb, there's about a half dozen or so different event demultiplexers that could possibly be used when you build the orb. You could have a Windows wait for multiple objects event demultiplexer. You could have a select-based demultiplexer. You could have a poll-based or dev epoll-based or KQ demultiplexer, and so on and so forth. And no one right size is right all the time. So we, of course, built a framework called the reactor that lets us plug in different demultiplexers. Well, the interesting truth is that in most applications, even though you might want the flexibility of having different event demultiplexers for different applications in a product line, perhaps, you only need one at a time. So rather than hard coding the software, instead we come up with some clever domain-specific language techniques we can use to annotate our reactor framework implementation so that when we know specifically the details of a particular event demultiplexing environment, we can automatically strip out all the extra virtual function calls and inheritance and indirection and replace dynamic binding calls with inlined calls that are statically bound. And this saves a good 5 to 10% of overhead on large amounts of data and large amounts of information that's sent across the system. And all kinds of similar techniques can be used for things like customizing the demarshalling and marshalling mechanisms, coming up with smarter ways to handle exception handling, and avoiding going through excessive numbers of layers multiple times and doing various kinds of pooling and caching and so on. So once again, patterns are really about looking for commonality and extracting it out of a world that can often be variable and finding ways to make the variability have a common interface. And so it's kind of exciting to see the whole field evolve away from simple design patterns to things that are also heavily optimization driven to allow not just behavioral and structural characteristics, but also quality of service characteristics and design expertise to be leveraged and improved.
Something you mentioned before was the term model and domain-specific languages and generation and these kinds of things. So most people probably have heard about the MDA, ModelDriven Architecture from the OMG. So I wonder how you use modeling and code generation, all these kinds of hype topics in distributed real-time systems.
That's a great question. When I try to understand this to myself and I try to explain it to other people, I usually start by pointing out that the last 40 years of computing have been an inexorable movement away from implementation and solution-centric ways of looking at the world, things that are bound up with computers and networks and very low-level things like register allocations and things like that, towards abstractions that are closer to the designer's intent. And if you look for the first 20 years or so, it was a movement away from very low-level platforms like hardware to operating systems and executives. If you can also think, of course, the transition away from machine code to assembly language to second-generation languages like C, that represents an abstraction away from the solution space closer to the application problem domain space. The problem is severalfold, though. Unfortunately, despite lots of advances in many ways, we're still kind of stuck in the following mire in a lot of these areas. In terms of platforms, we've managed to create much more sophisticated platforms that use frameworks and class libraries and components and so on in the terms of middleware. But those are now becoming so complex that very few people really have a lot of experience in making them work in the large. At the same time, the complexity of the platforms has drastically outstripped the complexity or the sophistication of programming languages that can be used to simplify the access to those platforms and the manipulation of the platform abstractions. So if you think about things like C++ and Java and C#, those are all clearly more, shall we say, in quotes, high-level abstractions relative to C or assembly code. But they pale in comparison to the kinds of complexities that can occur when you try to build these very large-scale systems using frameworks and middleware. And so what's really happened here is that language evolution hasn't kept up with platform evolution over the last, say, decade, or at least the last decade. A lot of my friends who do programming language research claim that there really hasn't been much of an innovation in programming languages over the past 20 to 25 years. So what do we need to do? Well, I guess one way to look at this is that the notion of a general purpose one-size-fits-all programming language that can be applicable to all different use cases and domains has kind of reached a point of diminishing returns. C#, Java, C++, and all the libraries that go along with those things represent kind of the last hurrah of that paradigm of development. And if you really want to go further, you have to start getting into much more domain-specific, much more vertical kinds of things. Well, there's a couple of different ways of going about this. The model-driven architecture approach was an attempt by the OMG to try to deal with the cacophony, the diversity of heterogeneous platforms and languages that has arisen, especially in the enterprise domain, over the past 10 to 15 years. And the goal there was to try to come up with some abstractions, things like structure diagrams to represent classes and their relationships, things like state charts to represent behavior and the transition between various kinds of control flows within systems, or the action semantic language, ASL, which is a way of trying to represent behavior again in a sort of an imperative-like way. And to do this in a manner that didn't really impinge on or didn't really have any particular binding to one platform or one language, to make things platform and language independent. And of course, the goal here was to try to make it easier for people to build systems that weren't going to be so wrapped up in the details of the underlying technology infrastructure. There are a lot of good things to be said about this approach. It tries as much as it can to leverage pretty widely understood things like the unified modeling language and the notions of syntax and semantics implied therein. But the problem with MDA, in my mind, is it doesn't really go far enough. It really provides just a small layer of abstraction and a slight distance and a raise of the level of abstraction away from building applications using third-generation languages with conventional platforms. True, you don't use C++ or Java directly per se, but what you program with, which is usually something like ASL, which looks for my money an awful lot like Visual Basic or Pascal, it's not that much different. It's not really raising the paradigm that much. Likewise, whether you use classes versus UML structure diagrams to describe the roles and relationships between the structure of your solution and your software architecture, it's really not that drastically a different level of abstraction. In a sense, what you're really doing is you're working with domain-independent modeling languages, or perhaps domain-dependent, but the domain is the domain of general-purpose computing. So you're not really raising the level of abstraction very much. And so while people have had some interesting successes in this area, I think a far more fruitful long-term direction is to use what's known as domain-specific modeling languages, which try to use various techniques such as meta-modeling, which is also often known as concept modeling, and the notion of domain-specific modeling languages that represent things more in the way that the users or the systems engineers or the domain experts tend to think about the problem, and capture them at a much higher level of abstraction. And then through some type of transformation engine or code generator or interpreter, create the artifacts that map onto the underlying levels or layers of abstraction, which could be middleware platforms, could be operating systems directly, could even be the hardware in some cases. And so you're left with many more degrees of freedom to go from the high level to the low level. Now, one of the things that's really important to recognize here is that with a domain-specific perspective, we're often not necessarily competing head-to-head with the traditional programming techniques for the kinds of things that programming techniques do well. Programming techniques such as Java or C++ or C# or even the action semantic language for that matter are pretty good at representing behaviors. Yes, you can come up with formalisms that are useful for certain very limited domains like state machines, but they're not that bad oftentimes to be able to characterize the control flow and the way in which information has to flow through a system. In contrast, however, there are an awful lot of things, especially in large-scale systems, where conventional third-generation programming languages are wholly unsatisfying and unsuitable for being used in any large-scale way. And oftentimes you don't realize this stuff until you've got yourself into a pickle by trying to build very large-scale systems where those systems have characteristics that you don't see if you're focusing on the trees and not the forest. For example, if you try to put together a system with 2 or 3 components, dependencies and deployment issues and configuration and customization issues aren't very profound. In contrast, if you try to put together a system with 1,000 or 10,000 components, you've got a major integration problem on your hands. And conventional techniques for dealing with this using XML or C++ or Java are very non-scalable for the main reason that they don't represent the solution in a way that represents a mapping back to the problem that's being addressed. So in those areas, domain-specific modeling languages, or domain-specific languages for short, are actually very satisfying and very suitable because they help to represent the specific information that's important for that level of abstraction, shielding people from things that they don't need to know about or don't need to know about in full detail at any given point in time, and allowing people to come back later and enrich and annotate further the information as they gather it. And so these domain-specific modeling languages are far more declarative than imperative, and they can take advantage of all kinds of analysis and synthesis techniques in order to reduce the probability of error through so-called correct-by-construction techniques, as well as to be able to greatly reduce the amount of code that has to be written manually by humans, but instead can be generated by an automated machine. This, again, should come as no surprise. We've been doing this for 40 years. If you think of a compiler for a language like C++ or Ada or Java that generates something for a lower level abstraction like 68,000 assembly code or a RISC instruction set, it's the same basic idea. It's just about going between levels of abstraction. Now we're moving the levels of abstraction further up towards the domain space as opposed to being stuck down in the solution space. I'm actually very excited about this particular perspective because I think we're getting to the point now where systems are sufficiently complex and people are trying to deploy them in sufficiently broad topology environments that it makes sense to really pay attention to some of these other issues that heretofore received somewhat short shrift from the development processes and tools and environments that we worked with. So I think we're getting to a point where this is quite exciting. I should also mention something else, that in addition to looking at structural and behavioral aspects of software, model-based approaches and domain-specific modeling languages are also increasingly relevant for dealing with issues related to the quality of service issues. And I'll give you a quick example. If you build large-scale systems that often have hundreds or thousands of people working on them for tens of years or dozens of years, and often have large amounts of infrastructure that has to be developed before the applications can be built, you run into what I call the serialized phasing problem, where you have this chicken and egg problem where you can't fully evaluate the performance and the quality of the infrastructure you're building until the applications are sufficiently done to exercise them. And of course, you can't build the applications until you've got the infrastructure fully developed, or at least enough developed that you could actually build the applications and run them. And this chicken and egg problem is actually quite serious for many large-scale systems, and I've seen many systems fail over time. The Iridium project comes to mind because they spent so much time building infrastructure that they didn't have a chance to get the applications done, and by the time they got the applications done, the infrastructure's flaws with respect to being non-scalable or error-prone or having problems with fault tolerance or security don't manifest themselves in a way that you can actually correct in a time and cost-effective manner. So one of the things we've been looking at lately is the use of model-driven development techniques and domain-specific languages for system execution modeling, which basically allows you to develop very quickly using model-based tools faux or sort of application component generators that can be assembled very rapidly to behave as though they were the real application components. And they have all the same properties you would have with the application components. They can have interfaces with ports. You can wire those ports together with modeling tools and so on. And you can put these things together very quickly to create experiments to run on the actual target infrastructure in order to be able to evaluate and ask kind of what-if questions. What if I arrange the deployment and configuration in a certain way? What will that do to my average and worst case execution time for the critical path? Where are the bottlenecks in the system? How many calls per second can I get through this particular part? What kinds of replication schemes work best under different loads and so on? And these techniques, which really only work if you have effective support for rapid prototyping of application behavior that comes from higher level modeling technologies, are crucially important in being able to get that information quickly. The last piece of the puzzle I'll mention in the space of modeling approaches has to do with combining modeling with model checking and static analysis of the software for various properties. One of the problems that's often plagued people who build C and C++ applications, and unfortunately, for better or for worse, most DRE systems today are still built with C and C++. They have a very hard time being able to do any kind of analysis of the code properties because C and C++ are rather uncivilized languages with all kinds of quirks in terms of pointer aliasing and memory corruption and other weird things that don't show up. And when they do show up, they end up causing havoc for analyzers of the software unless they're very, very sophisticated. And so one of the nice things about using model-based approaches is they can be far more civilized because they have better properties in terms of their semantics and the behaviors that they exhibit. And so as a result, you can do a lot more analysis on the models often than you can do on the code. And especially if you're able to then forward engineer the code from the models, then you can hopefully have better confidence that what you're creating through the constructive process will be more likely to be correct than today's construct by correction processes, where we build software by repeated testing until things break, and then we go back and scratch our heads and wonder how to fix it. So I think there's a wonderful synergy between model-based approaches and a wonderful synergy between patterns and frameworks and middleware. And just as the last 10 years has seen the synergy between frameworks and class libraries and patterns, as people got smarter about patterns, they got smarter about frameworks, they got smarter about middleware. I think the same thing is happening. As we get smarter about modeling, we're getting smarter about how we build middleware, and some of the quirks in middleware platforms can be shielded from developers, and it allows them to work at a higher level of abstraction that is ultimately more satisfying, although the jury is still out in terms of getting a lot of the accidental complexities wrangled out of that technology mix.
So, but you're not doing MDA officially, you're doing something different? Maybe 2 sentences of how you characterize that?
We're not really doing MDA in the executable UML sense. If you look at MDA as a technology standard, then we're not really doing MDA, the technology standard. If you look at MDA, the philosophy of building systems based with higher level abstractions that shield you from the details of lower level platforms and languages, we're definitely doing that. In fact, I think it's fair to say that the OMG over time has begun to realize the deficiencies with their initial MDA approach, and they've actually stood up a new special interest group called the Model Integrated Computing Special Interest Group. If you go to mic.omg.org, you'll find information about the MIC group. And they're actually looking at what do you do to come up with standards for model-driven development, model integrated computing, which is really more based around this notion of domain-specific modeling languages rather than domain-independent modeling languages, which is really what UML and executable UML are. Now, just a quick word on this. In order to keep domain-specific modeling languages and technologies from collapsing under their own weight, we ultimately have to get to the point where we have common, ideally standard tools and environments for building domain-specific modeling languages. If everybody has a different domain-specific modeling language and a different domain-specific modeling language environment, we're not much better off than we were 30 years ago when everybody and their brother had a different programming language, and they didn't interoperate, and they were very expensive, and everybody had their own little dialect that no one else knew how to speak or use. So I think that we're by no means done here, but I think we're going to see a great proliferation of domain-specific modeling languages as generator technology and meta-modeling environments get more mature. And from those explorations, we're going to start to codify good practice that manifests itself in terms of domain-specific languages for particular domains where people have enough critical mass to start to standardize what those things should look like. And there's a bunch of different efforts coming out of the Eclipse Foundation, coming out of Microsoft, coming out of a number of different open source groups, which gives me great confidence that we'll have enough of a community and enough of a experience base in place by the time that people are really interested in using this technology for real systems.
So before we finish off, I'd like to briefly come back to your hobby of being a professor for computer science. How do you integrate your students into your work? I always read papers from you that have a lot of students as co-authors, and they're integrated into all that ACE and middleware and research and practical research work. What's the way of integrating them?
One of the things my PhD advisor once said is the only way to be really successful as a professor is to teach the people around you how to do what you know how to do, so you can leverage their experience and their brain power and their time and energy in order to multiply your productivity. And so I've always been a big believer in trying to get my students involved in as many of the kinds of real-world activities that I've been involved in as a consultant and an author and a system developer and a researcher over the last 2 decades. We have the fortune of working with a lot of companies in our work. Many research projects tend to do things where they're funded by government sponsorship agencies that really focus on novelty, which of course is important in research, almost at the exclusion of practicality and transition. And while that's certainly a lot of fun, and we do some of that ourselves, I've often found it even more interesting and challenging and rewarding to focus on how you take those novel ideas and actually go the next step, which is to translate them out of the world of the ivory tower into the world of commercial practice. I find that there's some really rewarding challenges and some interesting opportunities that come as a result of that. So an awful lot of our research funding comes from working with companies like Siemens or Qualcomm, Cisco, Veritas, Symantec. We've worked with most of the telecom companies at one time along the way or another. We've even worked with Microsoft at various points. We've also done a lot of work with companies like large-scale system integrator companies like Boeing and Raytheon and Lockheed Martin. And doing this gives the students a much deeper appreciation of what really has to get done in the real world to take these ideas out of the laboratory and off the paper website into the actual code. We've also been very fortunate that we built up a huge body of software, and there's a lot of people who aren't my grad students, but are people who are part of our community of open source middleware and modeling developers and users who contribute substantially in order to be able to provide a good role model for the students. So the students learn very, very early on the importance of quality control, using build environments, using source code control systems, not breaking the builds, using things like distributed continuous quality assurance to run their code on many different platforms before they commit it to make sure the software works. And having an open source community where there are literally thousands of people around the world who will quickly find your flaws in your software and beat you back into submission to fix it has been quite an educational experience. And I think a lot of the students, when they graduate, come away with much deeper appreciation than the average graduate student would about what needs to be done in the real world to make stuff work. But of course, because they're researchers and they're rewarded ultimately by the quality and the quantity of the papers and the ideas they produce, they're also kind of pushed in that direction as well. So I think this is a very good thing. The other thing that I should mention too is that at least in the United States right now, in general, there's a downturn in the number of people going into computer science. There's a perception, probably somewhat misguided, that somehow all the good jobs are being outsourced to other places with lower labor rates and stuff like that. And while it's certainly the case that the general purpose computing jobs are probably going to places with lower labor rates, it is also the case that the mission critical systems, the systems where you bet your business, where you have life and safety critical and mission critical objectives that must be met without fail, where the right answer too late is the wrong answer, those kinds of jobs have a tendency not to be offshored and outsourced so glibly. And what we're finding is that students who have those types of expertise are quickly snapped up by all kinds of different people because there really isn't much more. There really aren't many places that are producing those kinds of people, number one. And number two, there's a tremendous demand within the United States, and I suspect also within other countries like Germany and in Europe, for people with very deep expertise in things like mission-critical, safety-critical, distributed real-time embedded systems. So what I always tell my students is these domains may be a little harder. You may have to work longer hours to become an expert and master them. But the good news is you're a lot more recession-proof and you're a lot more outsourcing proof when you have those kinds of skills. Thomas Friedman, in his book The World is Flat, talks about a job category he refers to as the untouchables. And he says the untouchables are basically people who, for whatever reason, are very hard to replace with other folks. He uses examples, of course, like Michael Jordan, the famous basketball player, or people who are great musicians or scientists as examples. But also, of course, you have people who are experts in their profession. And my experience has been that everybody who really learns through the baptism of fire in an environment that pushes both novel research ideas and the transformation of those novel ideas into real systems that actually work are often in very good position when they graduate. So we've been pretty fortunate being able to attract very bright people because they realize that this is a good investment in their long-term career path.
Last question, short one. Many of your projects are in the defense area. Many of your slides show those jet fighters and stuff. Have you ever had the chance to fly in one, and would you like to?
Actually, I've never had a chance to fly in a real one, but there's some really interesting flight simulator software that you can get access to that makes Flight Commander by Microsoft pale in comparison. There's a couple of domed simulators that they have in places like Boeing, and I've had the exciting time of being able to sit in one of those and fly those, and boy, is it amazing. What's even more exciting, of course, is realizing that our software is being used as the basis for a lot of that stuff. A lot of the distributed interactive simulation software in the world based on things like the HLA RTI, the high-level architecture runtime infrastructure, is all based on ACE and DAU. So it's very rewarding. But I remember one time one of my students who got his PhD recently went to Italy, and he's working for a company there that's basically building the next generation air traffic control system in Europe using ACE and DAU. And I always like to joke with him that I might take the train for a while until they get all the bugs out of the system. But they often say that there's no better proof of someone's confidence in their code than to fly with it. And I think we're no exception. But yes, we definitely try to do as many different things in different domains as possible. And of course, the places that are interesting to work are the ones with all the hard problems. So they tend to be the ones we focus on.
Okay, Doug, I really want to thank you for the interview tonight.
Thank you, Marcus. And thank you again for inviting me to spend some time with you tonight.
This concludes our interview with Doug Schmidt. Thanks for listening. I hope you enjoyed this show. For more information on some of the topics and abbreviations and concepts he talked about, take a look at the show notes. See you next week. This was another episode of Software Engineering Radio. For general information and past episodes, go to www.se-radio.net. SE Radio wants to thank Henning Pauli for providing the music we use in this show.